Okay, hopefully everyone can hear me. So can you guys just send on the chat if you can hear me? Hello? Okay. All right. Yep. So thanks for coming, guys. So we are having our MATH2501 and 2601 revision seminar part 2, and today I'll be covering the last 3 chapters of the course. So my name's Alex, and yeah, I'll be covering this part for T2 2020. So first up, we have just going through the overview of today's lesson, today's seminar. We're going to kind of summarize eigenvalues, eigenvectors, and look at the applications. So we're mostly focused on the rotation and decomposition of matrices of vector space, and also a 2601 topic of singular value SVD, so singular value decomposition, and then moving on to Jordan form and matrix exponentials. So feel free to ask any questions on the chat. I should be responding to it immediately. And these slides are beautifully created from previous year's Rui's and Kabir's slides. And so credit to them to help out, like making the content. Okay, so first we're going to talk about eigenvalues and eigenvectors. Essentially, the definition is covered before in first year as well, but let's just recap it. So if we have a linear transformation, we want an eigenvector is a vector such that upon transforming under the linear transformation, it will be equal to the scalar multiple of the vector, and the eigenvalue is that scalar multiple. Okay, and then we also have the definition of spectrum, which is just the set of eigenvalues for a linear transformation T. We also have something called the invariance. So a linear transformation is said to be T invariant if you have a vector that composes onto T and you end up back in the original set. So eigenvectors are essentially something that satisfies this property. So yeah, we have eigenvalues of T. So properties of eigenspaces, we have obviously eigenvectors are something that TV equals to lambda V. It satisfies this property. We also have the set of eigenspace as the set of vectors that are inside the kernel of this thing lambda I minus T, which is essentially if you just rearrange this part of eigenvalues dot point one, you get back the set of vectors such that this is true. Yep. And then also, if there are two, so third part is eigenspace at T invariant, which is pretty much that part I've covered before. And part 4, if lambda and mu are eigenvalues of T and they're distinct, okay, they're different, then it's said that the eigenvectors, okay, are going to be mutually exclusive, so not sharing the same eigenvectors for different eigenvalues. Okay, and then the part 5, it's pretty much a change of basis definition. So this part will kind of elaborate with more examples, but essentially these are the properties of eigenspaces. Yeah. So let's bring on to part 5. We're going to kind of like elaborate on what it means to use eigenvectors. Essentially, the most important part about eigenvectors is that you can diagonalize a matrix. What that means is you can transform a matrix such that you'll end up with a row of eigenvalues. Okay, sorry, a diagonal of eigenvalues, and everything else is filled with zeros. And then the matrix that transforms that is the matrix of eigenvectors. So we'll see that in a later example, but essentially this is these three properties is the property that defines why we can use diagonalization. So distinct eigenvalues correspond to linearly independent eigenvectors on each of the matrices. We also have the eigenvalue lambda. Yeah, V is an eigenvector of T with eigenvalue lambda if and only if the change of basis with respect to the new basis B is also an eigenvector of T with eigenvalue lambda. Essentially what that means is if you apply a change of basis with the eigenvector with the basis of B, then you get like a matrix that is with respect to the new eigenvectors as the new basis, and that is the diagonal matrix. Okay, so let's look at how do we find eigenvalues, because that's one of the most important thing in your test. So we're going to cover the concept of characteristics polynomial, and we're pretty much going to use that to find some eigenvalues. Okay, and then afterwards, given that we have more advanced examples, we can like avoid using characteristics polynomial later on. Okay, and then there's one last bit of theory, and then we'll cover some examples. So this is something called algebraic multiplicity, and essentially there's two types of multiplicity that we want to look at. Multiplicity is basically how many eigenvalues are in a matrix A. Okay, and if you have A as the matrix of that you want to find the diagonals of, then algebraic multiplicity is number of eigenvalues in the number of roots in the characteristics equation. Okay, number of roots in the characteristics equation. Whereas geometric multiplicity is the dimension of this kernel over here. Okay, so in this chapter 5, geometric multiplicity is going to equal to arithmetic multiplicity. That's it. Okay, but in chapter 6, this is not going to hold, and we'll see what are the results of that. But generally, geometric multiplicity will be less than or equal to arithmetic multiplicity, and we will see that later on when we apply this concept in chapter 6. All right, so I'll give you guys a moment to take a look at these eigenvalues and eigenvectors, and take a look at these matrices, and I want you to compute the eigenvalues and eigenvectors for me. Okay, I'll give you guys like roughly maybe 10 minutes or 5 minutes. So I'll come back at 4:14. And in the meantime, feel free to ask any questions if you have any. All right, so okay, I think maybe by this time you guys would have done question 1, perhaps question 2 as well. So either way, these examples aren't too hard. They are the basic application of characteristics polynomial. So we just need to find, our goal here is to find the eigenvalues and eigenvectors. Now, to find eigenvectors, you need to find eigenvalues first. Okay, that's generally the case. And pretty much all you need to do is take the determinant of this thing minus lambda I, okay? And that's how you get characteristics polynomial. And each of these questions are exactly the same. So let's see how we're going to do that. So first part, if we just take a look, right? We're going to let lambda 1, so we have this matrix 1, 2, minus 1, 4. We're going to have 2 eigenvalues. And okay, so here we pretty much avoided we pretty much guessed the solution to the eigenvectors by looking at this property. The determinant of this matrix equals to the product of eigenvalues, and then the sum equals to the trace. So this is one method of doing this. So the determinant of, and I guess like essentially you're bypassing the characteristics polynomial method. But if we were to use characteristics polynomial, I think it would also be quite simple. So let's see. All right. So essentially it will be 1. So we want to solve this matrix, the determinant of this. And then minus 1, 4 minus lambda. Okay, like that. And then this matrix is, so that's a 4. And this matrix, we want to find the determinant of this. Okay, and this, and this equals to 0. Okay, setting this equal to 0 essentially finds the kernel of, essentially solves for the kernel of a minus lambda I, but in the sense that we're only solving for the lambda values. Okay, so computing this is pretty straightforward. You just take the determinant formula, which is a d minus b c. Okay, and that setting that equal to 0 would do. Okay, and solving for lambda. So each of these questions are essentially the same thing. You just need to compute the determinant and then solve for lambda. Now the second method, which is what we showed over here, is kind of using a property that we will also be using later on, which is the trace and the product. Sorry, trace equals to the sum of the eigenvalues, and then the determinant equals to the product of eigenvalues. And you'll get 2 equations which you can solve for 2 unknowns. Okay, and after that, so that's 2 methods of finding eigenvalues. And then after that, to find eigenvectors, you essentially substitute, okay, your 2 into this equation, and you'll end up with minus 1, 2, 2. Okay, minus 1, 2, 2 over here. This is your this is what happens. This is your a minus lambda I, and your a minus lambda I, sorry, your a minus lambda I, this thing, you need to find the kernel of that. Okay, and that is, the kernel of that is the set of, so if you guys don't remember what kernel is essentially the set of vectors such that a minus lambda I times vector v is 0. So essentially this V is going to be our eigenvector, and in this case it's 2, 1. And we can do a similar thing here. So find the kernel of this matrix, okay, and then we'll get 1, 1. Yeah, and the next three, I will leave that for you guys to do. You can see that there are some complex, you can also have complex eigenvalues as well, because even though this matrix might look like a real matrix, but the solution that you're solving for the characteristics polynomial can be a complex solution. So you will get complex vectors as well. Okay, so next up we have the example on arithmetic multiplicity and geometric multiplicity. And we want to find AM and GM for each of these. So remember, AM is let me just rub this out. So AM is the number of solutions to the characteristics polynomial, and GM is the number, is the dimension of the kernel. Okay, so for the first one, right, you have two lambda values. So there are these two roots are going to form 2 AM. Okay, and for geometric multiplicity, because the kernel of this is also going to be, there's going to be two, yeah, so each of the dimension of, remember the definition of the geometric multiplicity, it's basically each of the lambda values, there's one dimension of kernel, okay, and so the dimension here is 1 and 1. So yeah, for each of the eigenvalues, we're going to get 1 for geometric multiplicity. And we can see that the other two examples are exactly the same thing. So lambda, there's one value, and then kernel, there's one span, all right, one vector as the span, which is pretty much, if you guys don't remember what span is the linear combination of this, but there's only one vector, so it's just scalar multiple. Okay, so scalar multiple of 2i1. Yeah, so multiplicity is rather straightforward. Now the interesting case is, I guess, oh, actually for part 4 as well, you can see that arithmetic multiplicity equals to geometric multiplicity. In fact, all four of these matrices have the same AM and GM, just because they're diagonalizable. Okay, each of the eigenvalues would have a corresponding eigenvector, and that corresponding eigenvector would have the same kind of nullity as well. We just say that each the kernel of a minus lambda I for that particular lambda is going to have a dimension of 1. Okay, so how do we know, in general, how do we tell that arithmetic multiplicity and geometric multiplicity is equal? We just need to look at how many times the roots occur. Okay, so if these roots, if there are a double root, like as in lambda equals to 2 and lambda equals to 2 again, that's when you need to look at like whether geometric multiplicity is equal to arithmetic multiplicity, and you can only check that. We'll expand more in Jordan form, but that's pretty much like the idea. If there are distinct roots for everything, you're only going to get equal multiplicity for each root. Okay. Yeah, next example, we have, so use the following information to find all eigenvalues and eigenvectors without calculating the characteristics polynomial, and then write the AM and GM for each eigenvalue. So we're given that 2 and minus 3 are eigenvalues. What are all the eigenvalues and eigenvectors? So here, this example, if you look carefully, right, if you're given 2 eigenvalues, you can pretty much use the idea of the property of the trace. So trace of trace is the sum of the diagonal elements. That has to equal to the sum of eigenvalues. In this case, we're going to have 3 eigenvalues, and so we're going to add 2, 8, and minus 7 and equate the 3. Okay, so your lambda 3 is going to equal to 2 plus 8 plus minus 7 minus 2 plus minus 3. So arithmetic multiplicity is 1, and then geometric multiplicity is greater or equal to 1. Okay, so that's from the property that we've described earlier. And since geometric multiplicity is less than, AM is less than or equal to GM. Oh no, AM is greater or equal to GM. Okay, remember that. So if multiplicity is 1, then GM is 1. And then to find the eigenvectors, I guess like it's sort of just taking the kernel of this, C minus lambda I for lambda equals 2, lambda equals minus 3, and lambda equals 4, and solving for that. So there's not much tricks to that, so we omitted the solution here. All right, and then next part, you're given the eigenvectors. Now you want to find the eigenvalues. And to do that, right, you need to find the eigenvalues first. So you can pretty much do that quite easily by just multiplying your eigenvector into this thing and then see which scalar multiple it is. So 101, if you multiply it in here, you get 303. And that's why lambda is 3. And then if you multiply 2 minus 1, 2 into that, you'll get the exact same thing. So lambda is 1. So your eigenvalues and your eigenvectors are going to be 3 and 1, and then you can just use the trace property to find the last eigenvalue. Okay, and that's pretty much it. So yeah, to find the vectors, eigenvectors, eigenvalues is pretty much using just the 3 things that you really need. It's characteristics polynomial, trace, and then using AM greater or equal to GM. All right, and just understanding the definition, A times V equals to lambda times V. All right, A times V equals lambda times V. All right, next we have the conditions for diagonalizability. So this part is kind of what we touched on before as well. If something is diagonalizable, there is a basis for V. Okay, so that's not going to, that is true, but it's not going to be something that you're going to use to prove something. Prove if is diagonalizable. But third part also, V is the direct sum of eigenspaces, so that's just kind of like taking a disjoint union kind of thing of the set of eigenvectors. So that's also true, but it's not really useful. But the last one, sum of geometric multiplicity of distinct eigenvalues, is the dimension of V. So this part is what, like the last part is pretty much what you need for diagonalizability. Let's look at this example to elaborate. So if we have a V vector space and there's V1, V2, V3 as the basis for V, then and we have this linear map, right? Is there a basis for V such that T is going to give a so basically, is there a diagonalized matrix? That's pretty much what this question is saying. So to get that, we need to convert TV into the matrix, okay, into a matrix of in terms of A times V. So that's the kind of the linear transformation matrix. And this A, all right, we want to find if this is diagonalizable. So first we're going to compute the characteristics polynomial and then find the eigenvalues, and looking at the kernel of each eigenvalue, we'll end up with the dimensions. Okay, so GM of 1 is AM of 1 is 1, right? Because there's one root. So now GM must be less than or equal to AM, and GM must be positive, so GM must equal to 1. All right, one root, one kernel. Sorry, dimension 1 for the kernel. Then for 2, you're also going to get GM. So AM is 2 because there's 2 roots. And taking the kernel and checking the kernel, we'll see that this also has dimension of 2, right? So that means the dimension, or the GM for 1 and GM of 2 is 1 and 2 respectively, and if you add them is 3, which corresponds to this part, okay, the sum of the dimension of the entire linear space, the vector space. So therefore it's diagonalizable. All right, next part. This is a pretty important theorem actually, spectral decomposition, and you're going to use this in like statistics and I think in many optimization problems. And it's to say that if there is a real symmetric matrix, then not only can I decompose my matrix uh, into a diagonal matrix. So normally, let me elaborate a little bit. So normally, if you just have an ordinary like matrix M, you can, and it's diagonalizable, you'll get this thing, P D P inverse. Okay, where P is the vector of of eigenvectors, D is the diagonal matrix, and with eigenvalues on the diagonals, um, and then P inverse is just the eigenvectors matrix inverse. Now, that's for normal cases. For a real symmetric matrix, it's stronger than that. You can factorize A, or whatever that matrix is, into a Q D Q transpose. Okay, and that transpose Q. So Q is also so first of all, D is a diagonal matrix as well, but Q this time is a set of orthogonal eigenvectors. Orthogonal means they have a, sorry, Q is an orthogonal matrix, and an orthogonal matrix in linear algebra is something that has all columns as orthogonal to each other and has a length of 1. Okay, so all vectors in Q is orthonormal, right? So that's pretty much what orthogonal matrix means. And if that's the case, then the transpose of that matrix is the same as the inverse. All right, that's the property of orthogonal matrix. And so in here, um, all eigenvalues are going to be real for this A matrix if it's real and symmetric. All eigenvectors are going to correspond to the same eigenvalues as we've stated before, but they're also going to be orthogonal. In fact, they're going to be orthonormal. Okay, they're also going to be length 1. Uh, yeah, orthonormal. And then there also exists a matrix Q such that blah 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 blah. So that's pretty much the definition of eigenvalues and eigenvectors. Okay, so yeah, okay, I think this is a bit of a typo. Should be eigen. So A has n orthogonal real eigenvectors. Okay. Yep. All right. So let's look at the next example. Diagonalize this matrix using the characteristics polynomial 3, and then um, yeah, lambda minus 3, lambda squared minus 1. So clearly from this example, you can see that lambda has to be 3, 1, and minus 1. And solving, that's because we've solved this equation equal to 0 and then solve for lambda, right? And for each of the eigenvectors for these eigenvalues, we'll get kind of like 3 separate kernels which we solve to get the eigenvectors. So we'll get minus 201 for lambda equals minus 1, minus 311 for lambda equals to 3, and the other one is right over here, minus 3, 1/2, and 1. Okay, for lambda equals to 1, just got cut off. And you'll get a diagonal matrix like this. All right. Next part, this is a optional topic. So normal operators is the set of it's pretty much the looking combining inner products with the adjoint property, and so a linear transformation on an inner product space is normal if and only if the map commutes with the adjoint. So if you can kind of like swap the adjoint with the across the inner product, then we call that kind of like the normal operator. By the way, this is Math2601 is in higher, it's not in lower, so don't worry too much if you're doing 2.5. So this pretty much is a, yeah, you have, if if t is a normal operator, right, then tv is also going to be the same as the adjoint of v in terms of magnitude. And also t minus alpha is um okay, there's perhaps a typo over here, but I think this pretty much meant that if you transform t relative to any alpha times any field alpha, you're also going to get a normal inner products a normal linear transformation. And then finally, you have an eigenspace t with eigenvalue lambda, and that's also going to be the same as t star with eigenvalue lambda bar. Okay, so this is the property with inner product space, and essentially you're just looking at the how you can transform tu with v, and how you can kind of like invert that, and there is a normal property coming out from the relationship between this t and this t star. Okay, so yeah, it's a stronger version of this conjugation kind of property. Anyways, that's not too important because there's not too many examples to elaborate on that. But let's move on to the next bit, which is important actually, conics, right? And we pretty much want to graph a conic using our understanding of diagonal matrix and kind of like diagonalization using eigenvectors. And let's look at how we're going to do that. So we're going to use the spectral theorem, okay? Because most of the conic question that we're solving, okay, actually, in fact, all the conic question we're solving can be written in terms of a real symmetric matrix times by that xy vector and xy transpose. And basically, this is how we can use the property of diagonalization to convert this middle matrix into something that we can solve more easily. And you'll see how the geometric application of this is also very intuitive. So essentially, what we're going to do is we're going to transform this A, B, B, C real symmetric matrix into and decompose it into Q transpose DQ. Why is this true? Because in the previous part, right? In the previous part, we've learned that the real symmetric matrix A can be written in terms of Q D Q transpose. Okay. Okay, I think this part there's a bit of an issue. This should be T. Okay, so this is transpose here, and there shouldn't be a transpose here. So Q D Q transpose, and by letting x equal to Q transpose times xy, right? You'll get a new set of axes, X capital Y. Those new axes are going to be the axes that points with the eigenvectors, okay? Points along or opposite or perpendicular to the two eigenvectors that you're looking at. Of course, this is for 2D because we're looking at conic section in 2D, okay? Not in 3D. But we can do it in 3D in some hard examples. But let's look at this curve, okay? So 5x squared plus 4xy plus 8y squared equals 36. So I guess like if you've came from HSC and you've just done conics in 2019, you should remember that um, this is something that's not in the syllabus because it's not really in the right form. We always remember that ellipses are in the form of x squared on a squared plus y squared on b squared equals 1. And hyperbola is x squared minus, right? So how do we convert this? The question here is how do we convert this into the form of x squared on a squared plus y squared on b squared equals 1? Okay, because of diagonalization, we can actually make it possible. So how we're going to do that is we're going to reframe this question and just translate the expression 5x squared plus 4xy plus 8y squared into a vector, a row vector times by the matrix times a column vector. And if you just check the dimension of that, that's 1 by 2, 2 by 2, 2 by 1. So you end up with a 1 by 1 expression. It's kind of like a dot product version of, but for like a vector and a matrix inside. So this is x squared, 5x squared plus 4xy plus 8y squared. All right, so this equals 36. And first, we're going to decompose this 5228 matrix. And we can do that by using, by first finding the eigenvalues, all right? And then we're going to compute and then we're going to compute the eigenvectors, and we'll end up with this expression, so 4009, and then the two vectors like as such, all right? And now we're going to use the spectral theorem. Spectral theorem says that this matrix is going to be like this inverse matrix is the same as this matrix transpose, which is the same matrix because it's also symmetric. So you'll get, okay, so where did this root 5 come from? Because this matrix is not yet orthogonal. Okay, it's each vector is orthogonal, but not each vector is orthonormal. You have to make it so that the vector has a length of 1. And so to do that, we're going to divide by root 5 for everything on both this side. And notice this is going to cancel out because you're basically timesing a 1 over root 5 in this matrix, and then timesing a root 5 in the inverse matrix, which when you flip it, you're going to get 1 on root 5 for both sides. So basically, you've just converted this into the orthogonal matrix. And orthogonal matrix has that property of transpose equal to inverse, right? So inverse equals to this, which happens to be the same thing. Now, this step, you have a matrix times xy, and then you have a row vector times the matrix. And what we can do here is essentially make this into xy. Okay, so if we let xy equal, like capital X, capital Y equals to this, we'll end up with the equation that x equals to this thing, capital Y equals to this thing. And essentially what that means is the entire equation will just be summed up with 4009, and then with x, capital X, capital Y, and then capital X row vector, capital Y. And this turns into 4x squared plus 9y squared equals 36. Okay, so that, as we know in conics, is an ellipse according to with a, if you remember, can I make a new page? Ooh. Yeah, okay. Looks like maybe I can look at, maybe I make, okay. Looks like I can't make a new page, which is annoying. All right, that's all right. Okay, so 4x squared plus 9y squared equals 36 is x squared over 9 plus y squared. Oops. plus y squared over 4 equals to 1. Okay, and this is an ellipse with major axis 3. So capital X, major axis 3 minus 3. Okay, and the minor intercept 2 minus 2. Okay, major intercept 3 minus 3, minor is 2 minus 2. So major is the big one and minor is the small one. That's how that's how we normally understand it. So that's how we can graph this ellipse. Okay. Now we're not done yet, because this is in terms of the capital X, capital Y matrix vectors, and we want to kind of change that back into the normal vectors. So let me just rub that out. So the normal vectors is little x, little y, and we need to convert that back into, okay, we have this equation, x equals to 1 on root 5 times minus 2x plus y. So that's essentially a translation, okay, kind of a rotation, in fact, a rotation of little x, little y axes, and then changing that to big X, okay. And so the equation for, like, how do we know what's the new axis? We can pretty much look at it by letting x equal to 0, because now we're only going to end up with the y-axis. Okay, so if we let x equal to 0, you'll end up with the y-axis. That's pretty much how you can find the new axis. So if I write over here, all right, if this is little x, little y, what we can say is that capital X, letting capital X equals to 0 will give you the y-axis. All right, that's how we normally find the y-axis anyway. So letting and that equation is 2x equals to y, right? So this ends up with a y minus 2x plus y equals 0, which is just this line. Okay, so this line in fact is the y-axis. Now we don't know the direction of that just yet, and we can pretty much substitute a direction vector to guess that direction. So what I mean by that is, if I substitute x equals to 1, y equals to 0, and the other way around, we'll get back a negative value, which is this way, which is yeah. So if you substitute x equals to minus 1 and x equals to 1, y equals to 0, which is this vector over here, okay, you'll end up with I think x equals to minus 1 over root 5, and y equals to 1 over root 5. All right, so negative value for x and positive value for y. So pretty much we can interpret the direction of this thing as y equals to 2x over here, and the other direction we just apply a similar thing, and it's going to be perpendicular, so it's going to be over here. And all right, actually it's going to be negative, so let me just double check. So yeah, this is y equals to minus 1/2 x as the x-intercept, and so it's going to be like that way. Okay, and so essentially the matrix the new, yeah, so we have the two axes of ellipse, which is 2x and minus 1/2 x, and the intercepts is plus minus 3, right, for x, and then plus minus 2 for y, and we just need to work out the x-axis and the y-axis. Now we know that this is the y-axis, but what's the positive direction? And So let me just erase that, right? We have the positive direction for y. We can substitute a small value to determine that. So if little y is, yeah, if little y is 1 and little x is 0, that's going to give me the positive direction, right? So little y is 1, little x is 0. Yeah, and we'll end up with a 2 on root 5 and then a positive 1 on root 5. So pretty much we can determine that 0, 1 becomes 2 and 1, right? Sorry, 1 and 2. 1 and 2. And then with a root 5 kind of chucking around here. 1 on root 5 here. So pretty much this is the direction for capital Y, right? Because you're essentially having just the positive direction aiming at 1, 2. And we can do the similar thing with the other way, which is with x equals to 1, y equals to 0. And we'll end up with, I believe, this way as the positive x direction. Let me just double check. Wait, if x equals to 1, oh no, we'll get x positive direction for x is this way. Yes, that's it. So so now the entire ellipse is going to look like plus 3 here, and then 2 here, minus 2 here, and then minus 3 here. And we're going to sketch that. Okay, that's the ellipse. Yeah, and the orthogonal matrix. Okay, so this matrix over here, yeah, is so that's pretty much the answer to this question. And if we want to find the smallest and the closest and the furthest points, right, we just need to substitute the corresponding values of y equals to 2 into this equation and then solve for xy. All right, next part is the orthogonal matrices. So this is for a 3D vector, and essentially you're going to look at the determinants of this 3 by 3 matrix, and you want to find whether its determinant is plus minus 1. So what we're going to look at first is consider an orthogonal matrix, right? And we can always express an orthogonal matrix in terms of cos alpha, sine alpha, minus sine alpha, cos alpha. This is pretty much like a property that you can use because it's essentially representing a rotation by angle alpha. All right, and because it's orthogonal, you remember this cos squared plus sine squared equals 1, length 1, length 1, and then also each of them has dot product of 0. So this represents a rotation. And for 3D vector, for 3D of matrix, the orthogonal matrix is going to look like this. So you can always transform it into this if it's orthogonal. And the idea is, if we want to find the angle of rotation of a linear transformation, we need to first find the eigenvalue, and then we're going to find the trace, okay, according to the eigenvalue, and then match that to find the angle. But if the eigenvalue is negative, then it's going to be not only a rotation, but it's also going to be a reflection. It's going to flip the signs. That's why there's a negative 1. So let's look at an example. So given that you have a geometric, given that you have a matrix, we want to find the geometric description of what this matrix actually does to the vector space. And we're already given that the matrix has 3 eigenvalues, 1, minus 1, and I. 1, minus I, and I. So first we're going to look at the trace, okay? Because this is going to tell me if this matrix is in fact, well, first we're going to check if this is an orthogonal matrix, and we can check that by looking at each column. Okay, each column is going to add up to length 1. Sorry, the square, like the length of each vector is going to be 1, and also the dot product of each pair of vectors are going to be 0. And yeah, we're going to check that. And the easiest way, okay, so the easiest way to do that is just by taking the dot product and then checking the determinant. Okay, so I guess like similar thing, yeah, if you take dot product and then check the length of the vector, you're pretty much going to get your orthogonal matrix. Now, we're going to check the determinant as well. And how do you check the determinant? Right, it's a 3 by 3, so you need to use the good old kind of hit the matrix and then get the matrix and find the 2 by 2, break it up, and then add it all up. Anyways, so after we've done all that hard work, we get determinant 1. Now, we know that the product of eigenvalues is also the determinant. So if you take the product, right, you can actually get yeah. So you actually, okay, if you, the fast way to do this question is you just take the product of these eigenvalues because they're going to equal to the determinant. So, and if we know that the determinant is 1, that means the whole matrix didn't really rotate, didn't really reflect its axis. Okay, it just kept the same orientation, and it only rotated. And how do we check if it's how do we check the rotation? Just look at 2 cos alpha plus 1, right? How do we know that? This is, yeah, so over here, this is the matrix. This is the matrix that this is similar to. Orthogonal matrix with eigenvalues, with orthonormal vectors, right? And then we can decompose it and transform it to alpha and cos alpha and sine alpha. So doing that over here, you'll end up with the same trace. That's the property that we're going to use. So we're going to say that a matrix, if it's similar to another matrix, then it's basically it can be diagonalizable, or like it can be transformed and under a change of basis. So pretty much you just need to match this 2 cos alpha plus 1 with the trace. Oh, sorry, with the determinant. No. Hang on, sorry, with the trace, yes. And wait, hold up. Oh, no. Oh, yes. Okay, so let me take a step back. So the trace of this thing, 4, 4, and 1 is going to give you 1. All right. So that, yeah, you're going to match this trace with the similar matrix, with the trace of the similar matrix, 1, 1, and cos alpha. 1, 1, and cos alpha and cos alpha. So adding it up on both sides, you can solve for alpha. Now this alpha is in fact, I forgot to fix this typo. This should be pi on 3, I believe, because it's 1 minus, oh no, sorry, I fixed the typo before, yes. So this is pi over 2, right? Because cos alpha equals to 0, alpha equals to pi on 2. Yeah, so there's no typo here. All right, and then likewise, we can check the next part. So second question, if we're only given one lambda value, one eigenvalue, we're going to end up with a trace of, so the determinant, we're going to first check the determinant again. And this, okay, I think this I think there's a missing piece of information over here. In fact, there should be a minus 1. I think there's a, let me just, yeah, there is, so there is 2 extra eigenvalues that will be given in the question. Otherwise, you actually cannot solve this. And the eigenvalues are, I believe, something pretty complicated. It was actually, Yes, so it was a minus, I think a minus 1 plus minus 4 root 5. Anyways, there is a, yeah, so for this question in part B, you need the three eigen um, you need the three eigenvalues so that you can find the trace, and the trace is 1/9. And so now checking, if you check the other eigenvalues. Oh yes, so Marty asked the question, will they ever ask to describe a matrix that isn't a rotation? Good question. So if there is a matrix that's not a rotation, it will be with an eigenvalue, sorry, with a determinant of -1. Okay, so that's the answer. Yeah, and that's basically a reflection composed on a rotation, and that's how we can describe that. All right, yeah, and in this particular example, it's exactly that. So yeah, if the determinant is not 1 or -1, then it's not as simple as a rotation or reflection composed with rotation, but it's like a mix of transformations. And we can't really describe that afterwards. So you're only going to get two cases where determinant is 1 and determinant is -1. All right, and you just need to describe those. So yeah, anyways, back to this example. In fact, when we have one value that we know lambda is -1, we can pretty much get out the entire question because the trace is 1/9, and that means, yes, so that means that if the trace is 1/9, we have three eigenvalues, right? And the product of the three must equal to 1, and the length of each eigenvalue also has to be, the magnitude of each eigenvalue also has to equal to 1. But the trace is 1/9, which means if we kind of write this out, lambda 1 plus lambda 2 plus lambda 3 equals to 1/9, where each lambda value has a length of 1. For this to happen, lambda 2 and lambda 3 has to be complex numbers, okay? Which means they're not 1, which means the only value that we have over here, lambda, is -1. This is going to be the vector of interest. Sorry, this lambda value equals to -1 is going to be the the eigenvalue that tells us this is a reflection composed with rotation. And how do we tell what plane it is reflected by? We take the dot product of the corresponding eigenvector. So this is the eigenvector. All right, taking the dot product gives me the plane that it's reflected by. Because essentially you can think of it as like a 3D diagram. It went from this arrow pointing the other way. So the plane that flips that is going to be this plane, all right, where it's going to be perpendicular to this vector. Anyway, so the angle of rotation is given by this, and alpha is cos inverse 5/9. All right, next part. Next part we have a singular value decomposition. So this is a rather high, kind of like 2601 topic, and it's basically saying that any matrix can be decomposed into a unitary matrix, and then with m by m size, another unitary matrix n by n size, and then a sigma matrix, which is kind of the set of what we call a singular value. All right, and this is basically an extension of kind of what do you call it? The diagonalization, but for an m by n matrix, and we're taking advantage of kind of the property of a star a, which is the adjoint, right? So, oh yeah, and also singular values. What are singular values? They're the square root of an eigenvalue. Now, let's look at the algorithm to compute singular value decomposition. So first, we're going to look at the eigenvalues of a star a. and then write that number in descending order. Okay, so this step is pretty important because it needs to be normalized, and that's like kind of the convention to maintain the eigenvectors in the order that we want it to be. Now, yeah, and the next part we want to find the associate eigenvectors of unit length vi. And then afterwards, second step, we want to find an orthonormal set of eigenvectors with A star A. So that's essentially kind of computing all your eigenvalues and then taking the eigenvectors and then getting the unit length as well. And then we use the Gram-Schmidt procedure if there is any extra kind of if there's any missing eigenvectors. Okay. So yeah, so automatically occurs when all eigenvalues are distinct, and that's usually the case. But if there isn't, if not all eigenvalues are distinct, we need to fill it up with Gram-Schmidt. And pretty much we just need to compute the rest of this by using the UI as the new unitary kind of matrix, and it will transform your vector from 1 by n to 1 by m. Okay. Also m by 1. From n by 1. Okay. That's pretty much what this, sorry. Okay. So this is m by 1, and this is n by 1. Because a is m by n. So you're going to end up with that. All right, and then lastly, just kind of like list out your u's and list out your v's, but in the same order that we've listed out my singular values. So one quick trick that we can do is to solve for finding the eigenvalues of A star A rather than and putting it and treating A star as the same with the same eigenvalues. And what that can do is it will save up kind of like solve two birds in one stone, right? Because you're going to solve for not only A star A, but when you're flipping the two matrices together, you're in the later example, you can abuse the fact that they share the same eigenvalues. So first we're going to look at this matrix. All right, simple example for 2601. So 3 minus 1 1 3 1 1. Find the eigenvalues. We do that by looking at A star, which is A star, remember, is the transpose and the conjugate, right? Conjugate transpose. Take that, you get a real symmetric matrix. And then what we can see is that this matrix has, we can compute the eigenvalues, and I'll leave that to you guys. Now, because we know that A star A and A star have the same eigenvalues, right? Then we can just pretty much look at A star A, which is a 3 by 3 matrix. Okay, remember A is a 3 by 2, so 3 rows, 2 columns. And if you times A with 2 rows, 3 columns, so 2 by 3 matrix. And essentially we're using this trick of equating the eigenvalues for A star A and A star to save us the hassle of computing the eigenvalues for a bigger matrix. So eigenvalues here, or the E space here, the eigenvalues, the set of eigenvalues in here is going to equal to the set of eigenvalues in here. Okay. So we're going to simplify a lot of the calculations. So A star A will have the exact same eigenvalues, and then just plug it in. We can find the eigenvectors for 12 as well as the eigenvectors for 10. And so we get 2 eigenvectors, but this is a 3 by 3, right? So we need one more eigenvector. Otherwise, it's not complete. And to get that, we just use Gram-Schmidt's. Okay, so, or in fact, there is a we can use the trace property to. So if we look at this thing, minus 2, minus 10, minus 2, minus, oh no, sorry, 10, 10, and 2, you have 10 and 12 as your lambda. So adding 10 and 12 with 10, 10, and 2, these two are going to equal. And so 22 equals 22, which means your third eigenvalue is going to be 0. And kind of, if eigenvalue is 0, you can pretty much do a yeah, that's a big problem, right? Because you actually can't solve for the vector v, but instead you can solve for, or actually eigenvalue of 0 means it's kind of the kernel of, yeah, the lambda value is going to give you the kernel, sorry, the eigenvector over there is going to be the kernel of the matrix. So this, setting this equal to 0 and solving for this solution, yeah, will give you minus 1, minus 2, 5, which is the set of vectors that are the kernel of this matrix. Yes. And these three vectors with three, yeah, so in this case, we didn't actually have to use Gram-Schmidt's, which is kind of nice. But in other cases, you might have to. And so taking these three vectors and putting it into, so automatically you get the V matrix just by taking these three vectors. And remember, you also have to list out the eigenvalues in descending order as kind of a convention. So next part, we're going to compute U using the 1 over the singular value times A, okay? And you'll end up with two vectors, and then we just need to plug it in. And you get these two vectors as matrix U, the previous three eigenvectors as matrix V, and then the singular values listed in a diagonal with the remaining values as zeros, okay? And then this is singular value decomp. Yep. All right, next part is Jordan form. So Jordan form is a big topic, and pretty much it's an extension of eigenvalues where some of the roots are repeated and you actually have a different geometric multiplicity with the arithmetic multiplicity. And basically the idea is we can diagonalize any matrix, right? Sorry, we can diagonalize a certain set of matrix. We can also take the Jordan form of any set of matrix. And in many of the particular cases, you'll end up with you kind of get a special, sorry, it's kind of like a more general case of a diagonal matrix if you do not have the property that each eigenvalue are distinct. Okay, so when you have some eigenvalues that are like different, that are the same, and then you end up with multiplicity and issues like that, Jordan form is the way to go. So first, we're going to look at that by looking at Jordan blocks. And Jordan blocks are basically chunks that compose of a Jordan form. There's a Jordan matrix. And Jordan matrix is basically the disjoint union or the direct sums of Jordan blocks. Basically, what that really means is there's just going to be a whole bunch of blocks like that. And then the rest are zeros. And then, yeah, for your Jordan blocks, an ordinary Jordan block with a eigenvalue minus 4 is going to give you this, and it's size 3, right? And then Jordan block of size 4 with eigenvalue 0 is going to look like this. So the idea is if you raise Jordan blocks to a high power, it's actually really easy to compute because it kind of like follows the Pascal triangle kind of thing. So this is Pascal triangle layer 1, Pascal triangle layer 2, Pascal triangle layer 3, and so on in like a upper right hand corner kind of way. So yeah, it's it's really easy to compute Jordan form, and this is pretty much like compute powers of Jordan form, which is pretty much why we use this in the first place. And it goes on to like exponentiating a matrix and so on. Okay, so first let's look at the computing the powers of so this is pretty much what I just said just then. Matrix direct sum is basically what I've said about the blocks. And yeah, basically this is the most important example. So if you look at the direct sum of this block with the other, this block of J2, 3, you'll just have a block of size 2, right? Dimension 2 with eigenvalues 3, 3, and then you put it here, and then composed with a block of size 4 with eigenvalues 5, 5, and 5, and put it right there. And that whole thing is going to be the direct sum. So there is a lemma that says that if you raise the direct sums of each Jordan block, you'll get the sum of the powers of each Jordan block, and so direct sum of the powers of the Jordan block, which is a very powerful kind of lemma, because now you can use this to elaborate and expand higher powers without having to worry about kind of like the very annoying, nasty matrix multiplication. Okay, you can just use the Jordan block theorem over here in the past and raise that to a higher power and then plug it back into the equation without having to do the computation yourself. Okay, next part is what we call the generalized eigenvectors, and we use this in computing the eigenvectors for, or not really eigenvectors, but generalized eigenvectors for Jordan form. Okay, and we'll elaborate on what this is. But basically, it's kind of like it's the same thing, but you're raising to the power of k instead of the normal usual eigenvectors are just a minus lambda I times v. In this case, it's a minus lambda I to the k times v. And the reason why we have to use this is because some of the eigenvalues are going to it's going to have like repeated roots and so on, and you actually have to repeatedly multiply a minus lambda I to apply to get back into the kernel. Okay, so let's look at this question. Generalized eigenvector, and you have one generalized eigenvector, and you have one matrix, and you have the corresponding eigenvalue as 5. We want to find what is the what is the rest of this, what are the rest of the eigenvectors, generalized eigenvectors, and also the rest of the sorry. Show that v is a generalized eigenvector of this correspond to lambda equals 5. Okay, so pretty much there's not much to show here. If you just do c minus lambda I, you just end up with the matrix that you want to find the kernel of, and then you just multiply it with v until you get 0, and then you end up with 0, 0, 0, which means done. It's a generalized eigenvector. Okay, so normally this the other vectors are, I believe they won't end up with 0, 0, 0, but they'll end up with kind of like keep c minus lambda I will give like itself, and then you'll just end up with a non-zero solution, which means it's not a generalized eigenvector. Okay, and then there's this concept of generalized eigenspace, which is the collection of these generalized eigenvectors. Okay. Yep. All right. So now we want to get into the good part, which is the part that you're actually going to be tested, which is the Jordan matrix, making the Jordan matrix. Okay, that's what you have to do in the exam. And pretty much you just need to find the Jordan blocks. Okay, and the Jordan blocks are found by using the generalized eigenvalues and then the generalized eigenvectors. And basically there's some lemma saying that each Jordan form has is made up of, like, for each Jordan matrix there's one unique Jordan matrix, and if you've permutated all the Jordan blocks correctly, like if you order it in a way that in a fixed way, like descending order, then every matrix will have one unique Jordan matrix. Okay, and then this part is how we're actually computing the Jordan forms. Okay, there's a bit of a mouthful here, but pretty much what you have to do is to find something called the Jordan chain. All right, and this kernel A minus lambda I thing is basically um, a way of kind of like representing the chain. So if you start off with V, and then you kind of like get the V is the kernel, right, of A minus lambda I, and then you also want to repeatedly kind of apply that, then this theorem is kind of like showing that the kernel of the lower power is going to be subset of like the higher power, which eventually is going to equal to the entire vector space. Also, there's something called the arithmetic multiplicity, kind of like descending order. If we set, sorry, this is geometric multiplicity. So if the gm of a minus lambda I, all right, is going to not only follow a non-decreasing order as k increases, but the difference is also going to diminish to 0. That's pretty much what these two are saying, and we're going to use this repeatedly in the next few examples. Okay, and so eventually when this d equals to the arithmetic multiplicity, we are done. So that's how we compute generalized eigenvectors. Now I know that part is like perhaps pretty confusing, so let's go to an actual example, right? Um, okay, so this is the concept of Jordan chains, and we're going to pretty much essentially, I'll go back to this, and it'll make more sense when I go through an example. So let's see. So the first part, right, you have a matrix with C, and then you have an eigenvalue 5, which is the previous part. We want to find we want to find what is this kernel, and we want to find C minus 5i composed with V, which is pretty much this thing. Okay. Uh, sorry. We want to find the generalized eigenspace. Um, and then we want to continuously multiply that until we get 0. So this is what this chain is doing. All right. So let's see. All right. So C minus 5i V, C minus 5i squared V. That's done in the previous part. It's just this. It's just this 1 minus 1 1 and 0 0 0. But then in the next part we want to find all the eigenvalues of C if we're given the previous calculation. Okay, so first we're going to note that the algebraic multiplicity of the first one is at least 2. Now why is that? Because we know that GM is actually less than or equal to AM. And by doing all this hard work on the 5 minus C minus 5i times V and C minus 5i squared times V, we know that this equals to 0, right? The second one equals to 0. So if the second one equals to 0, GM is at least 2. Which means, GM equals to 2 because it's equal to 0, and the previous one doesn't equal 0. And AM is at least 2. And if AM is at least 2, then the third eigenvalue is going to be either 5 or something else. All right, but second eigenvalue would be 5, and so is the first one. So by using the trace property, we're going to use this a lot. So trace eigenvalue 5 plus 5 plus some random lambda equals to 13. So lambda is 3. So the third eigenvalue is not the same as the first eigenvalue. And so using that property, right, 3 equals to using 3 over here, we can end up with eigenvalue of 5, am is 2. Now gm is in here. Gm is actually okay. Gm is 1. Now gm is 1 because if we look at the if we look at the dimension of the kernel, right? Dimension of kernel of 2 is equal to 0. So the only dimension of kernel of 1 is going to equal to 1. So I believe, yes. So the gm over here equals to, yeah, if gm over here equals to 1, then that means um, the way we've calculated the eigenvalue would have been using a different method. Just kind of we know that we know that c minus 5i times v is equal to a non-zero number, and we also know that c minus 5i squared times v is equal to the zero vector. So c minus 5i to the power of 1, which is over here, okay, is the nullity of that is a dimension 1, yes, a dimension 1 vector. So that means, that the algebraic, okay, so the geometric multiplicity, sorry, my bad, over here is actually 1. But to know that this is the second 5 over here, we use the previous part. Okay, we use part 1 to solve for, I believe the second lambda value, or it was told in the previous part for us to determine that. Now, yeah, we have 2 GMs, so GM equals 1 for the first part, and then obviously the remaining bit, if the arithmetic multiplicity is 1, geometric multiplicity, the remaining geometric multiplicity has to equal to 1 because it's less than the AM. All right, and then finally we just need to take the row reduction of across the smaller eigenvalue, and you'll end up with the third eigenvector. Finally, we just need to put everything back together. So we see how our Jordan chain has, we start off with the first Jordan chain, 1, minus 2, minus 3, and then minus 1, 1. So now we just need to put it in reverse, like this, and then put the Jordan block in the corresponding position, 5, 0, 1, 5, and then do the same for the next Jordan block, which is a single value 3. And that gives me our P matrix, which is the set of generalized eigenvectors, and J, which is the Jordan matrix. All right, and then we have the second example over here, which is rather similar. I'll quickly go through that. So essentially, we have 2 generalized eigenvectors, okay? Sorry, we have 2 generalized eigenspace. So for lambda equals to 2, we have a span. All right, this time around, by the fact that it has a span of 2 vectors, the dimension of the kernel is actually 2. So straight away we can tell that GM is 2. Okay, and this one GM is 1. And then find the Jordan chain starting with 0, 1, 1, which is one of the vectors. So what are we going to get? We get 0, 1, 1 composed of a minus 2i. We'll get another vector, which is exactly the linear combination of, so get back into this generalized eigenspace, and then you compose again, becomes 0, 0, 0. So over here, the algebraic multiplicity is 2. But since we have another distinct eigenvalue, so geometric multiplicity is less than or equal to 2. But geometric multiplicity is not 2 since we have a chain of length 2, so GM is 1. Okay, so So the generalized, yeah, the GM of this equation. Okay, actually, sorry, this bit should be 1. Um, so so if we look at the arithmetic multiplicity, yeah, if we look at the geometric multiplicity of the second part, right, we have a chain of length 2, and so pretty much we can have a by the previous lemma, right, that says yes. So if um, the arithmetic multiplicity of an eigenvalue lambda equals to the dimension, okay, and we can see that the dimension over here actually just equals to um, the very last eigenvalue, sorry, the very last value that gives me a non-zero, the very last value of k, such that the nullity is not 0, such that the nullity stops increasing. Or yeah, so our GM over here in this example is in fact 1. Okay, so for this block is 1, and for the next block it's also very, for the next block, which is the other vector 1, 4, and 2. If you compose that onto A, you just end up with 0. So pretty much you'll end up with this matrix 1, 4, 2, 0, 1, 1, minus 1, minus 3, minus 2. Okay, just by flipping this left to right, flipping this left to right. Finally, we have the example 2, which is the generalized eigen. If we have two vectors that are in two different generalized eigenspace, we want to find them such that it equals to 2, 1, and 0. So building on into this example, okay. So GE2, GE3. So how do we do that? If we just look at the linear combination of um, any three of these vectors, okay, since they're linearly independent with one another, any linear combination of this will give me 2, 1, and 0. So this is just pretty much a linear independence row reduction question. Okay, nothing more fancy than that. If you just solve, right, for this matrix equated to this, and then solve for the corresponding values, you get 3 minus 4 minus 1. And then you just add the two vectors that are in the same generalized eigenspace, and you get the answer. All right, so that's pretty much a recap of generalized of Jordan form, and essentially there is, oh sorry, there's one more. So but yeah, that's to look at the computation of Jordan forms and finding how to get P, J, and you don't need to look at P inverse. You can always write P inverse as it is. So that's really good. Yeah, you essentially just need to find how to get Jordan blocks. So I'll pause here to ask if there's any questions. Okay. Um, in that case, I'll continue with the similarity invariance. So basically, yeah, if two matrices are similar with one another, they will have the same Jordan form. And that's pretty much the main gist of why we use Jordan form, because um, we can convert, well, it's one of the key properties of determining whether two matrices have like a similar property, which is really nice. So like similarity is kind of like similar triangles, but like it's for matrices, and there's a lot of it's expressible in terms of like the same bases and sort of thing. It's not a scalar multiple, but it has this PBP inverse property. All right. Next part, I think we're gonna look more into how do we find Jordan forms based on other information. So given that we have some nullities we want to find all possible Jordan form. So the idea for this is to use an onion diagram. And what an onion diagram essentially does is we'll look at how many vectors, okay, how many eigenvectors are inside the first kernel, and then how many eigenvectors are inside the generalized eigenvectors in the second kernel, and then in the third kernel. Okay, so because the nullity of b minus lambda I is 5, that means we know that there are like 5 vectors. That means when we compose b minus lambda I, which is a 10 by 10 matrix, there's going to be 5 rows of zeros. So 5 rows that such that it's 5 rows of linearly dependent vectors. And so you'll first sketch a layer of the onion diagram like this, okay, to represent that piece of information. And then the next step is to look at the kernel of b minus lambda I squared. And because nullity is 8, that means there's 3 extra vectors coming from between b minus lambda I to b minus lambda I squared. And that's represented by these 3 vectors. Okay, so first you sketch out the 5, and then you sketch out 3. Okay, because you compose once more, and that's going to end up with in the new kernel of b minus lambda I from b minus lambda I squared. Okay, and then you compose one more time, and then you have only one vector left. Okay, and that's 9, the last vector. So now the question is, what is the Jordan form based on this? Well, we can pretty much use this to determine the Jordan form because we have one Jordan chain, okay, one Jordan chain, 2 Jordan chain, 3 Jordan chain, and then 4, 5. Right, and then the last one, I believe it's going to follow. It could be, so there are 2 cases for the last one. Either it's in this Jordan block or it's not in this Jordan block. If it's in this Jordan block, we'll just continue on with this longest vector. If it's not in this Jordan block, we'll just find a separate eigenvalue. So the 10th eigenvalue is not lambda. Okay, so that's our first case. That means this lambda is this is all the generalized eigenvectors that we can represent. So that means there is a block of size 3 coming from this length over here, a block of size 2, 2 blocks of size 2 in this length over here, okay, in this over here, and then 2 blocks of size 1. All right, that's how we can use the onion diagram to sketch out all possible Jordan blocks. And then the last bit, there's only one eigenvalue, so there's going to be a block of size 1 for a new eigenvalue lambda, for new eigenvalue mu. Okay, so that's for case 1. There's also a second case. So if the 10th eigenvalue is also lambda, that means that you're going to have a new block. So actually, you have to be super careful here. So can we have a eigenvalue that is, let's say, can we have a new generalized eigenvector that's here? Well, if this is 5, okay, and then this next dot, if it's in the, so there are, okay, let me take a step back. So if there is a 10th eigenvalue, this 10th eigenvalue would have to be in either one of these kernels, okay, b minus lambda I, b minus lambda I squared, or b minus lambda I cubed, or b minus lambda I to the 4. Now, if it's in the first one, then that means this would be 6, okay, and that's not true. The nullity is 5, so it can't be in the first one. Can it be in the second one? So if it's in the second one, the nullity of b minus lambda I squared should be 9, but it's 8, so that's not true either. it's not in the third one, because the total nullity of b minus lambda I cubed is 9. So it has to be in the fourth one. And for it to be in the fourth one, it must follow. So if I sketch the Jordan diagram again, 9, 5, 3, and then 1, right? So it can't be in any of these shells. That means it must be outside. If it's outside, then it has to be connected to this one, which is connected to this one, which is connected to this one. Okay, it can't be connected to another. It can't connect straight here. You can't do that because for it to connect straight here, that means the kernel of b minus lambda I cubed must also equal to 0, because b minus lambda I to the 4 is equal to 0, which means there is another vector here, but there's no vector here, so that's not going to work. So the only possible case is for this to be in the same Jordan chain, which is why there is a J for lambda. And then the rest stays the same. So this is pretty much what the proof by contradiction is doing. Okay, and now next part is checking is the other way around. So tell me if this is a possible configuration of nullities. And essentially, this cannot happen because this is 3. So going from this to this, there's 3 vectors. Going from this to this, there's 1 vector. And then going from this to this, there's 3 more vectors again. So this does not happen for onion diagram, because if you draw 5 here, right, and then you draw 3 more here, and then you draw 1 more here, you cannot possibly have 3 more again on the outside, because you cannot if the kernel of that equals to 0, you can't find any other vector in this onion diagram for it to form a Jordan chain. So this cannot happen, and so this is false. Okay, so yeah, so pretty much that's that. And then we have a kind of a next question, which is given a Jordan block, a Jordan form configuration, find what is the nullity. So of a plus 4i k and a minus 5i to the k. Yeah, so to do this question, we just need to list out the Jordan block for Jordan form, the onion diagram, okay, but in reverse. So there's going to be 2, 2, 2 like this. So clearly the nullity of a plus 4i to the 1 is going to be, so if there is a Jordan block of size 2, that means the chain is of length 2. So this is representing a chain of length 2, a chain of length 2, a chain of length 2, and you'll pretty much get 2 particular kernels that you're looking at. So kernel of a plus 4i, and then the kernel of a plus 4i squared. And so you get 3, so nullity of a plus 4i to the power of 1 has 3 vectors, so it's dimension 3. Okay, so k equals 1, it's 3, and then k equals 2 and onwards, it's going to be 6. And then for this a minus 5i to the k, we can apply a similar trick. So 3 vectors in the first block. Sorry, there is a length 3 Jordan chain, right? There's a length 1 Jordan chain here and length 3 Jordan chain here. So length 1, and then a length 3, a separate length 3 Jordan chain. So the nullity of this would be, so first case for a plus 4i to the k is going to be first 3 and then 3 and 3 and then 6 and then 6. The next case, it's actually 2 and then 3, then 4, and then stays as 4. Okay, so yeah, that's pretty much the diagram that you just need to draw, and then you just plug it in here, and that's pretty much the rest of that answer. All right, finally, we have matrix exponential, which is the final topic. I think for 2501, it was only covered up to like the exponential part. You don't need to solve any homogeneous system of equation, but 2601, you might have to do that. So I'll cover both, but you're free to kind of like not listen, I guess, if you're doing 25 towards the last part. Okay, so this part is still in 2.5, okay? So exponentiation of a matrix is conveniently, it's if a matrix A equals to PBP inverse, then the exponentiation of that matrix is going to be P times the exponential of exponentiation of B times P inverse. And then the direct sum property also holds. And so and we have this final property, which is kind of the equivalent of exponentiating a Jordan block. And we can see that because Jordan block has, sorry, the Jordan, because Jordan block has one, so all these eigenvalues with lambda, and then we have um, all the kind of Pascal triangle expansion, then the exponentiation of that is conveniently this kind of Taylor series looking expansion. Okay, so this exponentiation of Jordan block will end up with this expression, and this expression is it basically looks like a Taylor series of your original block, because there is a very nice kind of, because if you put the lambda values, right, kind of like that, and then you put ones here, exponentiating this thing is kind of like exponentiating lambda plus 1. Okay, and then to the power of n, so all the coefficients just come out, and then like this turns into a this turns into all these kind of coefficients of t squared on 2 factorial, t cubed on 3 factorial, and so on. Okay, so let's look at how do we exponentiate tc, and to get that, we look at we first need to find the Jordan block, okay, Jordan matrix, and then the P matrix. Okay, so this is the same matrix as a previous example. If we want to exponentiate TC, we just need to apply this property, okay, exponential. So first we take the exponential of the Jordan form, which gives me this raised to the power of e to the 5t, t e to 5t, and e to 5t, e to 3 cube, e to 3t, and so on. So how do we get that? This comes from previous part over here. Okay, if it's any higher power of Jordan block, remember there's a t squared on 2 factorial, or like a t cube on 3 factorial. But in this case, it's just like a t, because it's 2 by 2. And then taking the exponentiation of c, you just have p times this exponential of j times p inverse. Now, the question is, can we get p inverse? And the answer to that is we actually can't be bothered, because no one's going to do an inverse of a 3 by 3, let alone maybe even bigger matrix when you're looking at it. So we actually don't really need to do that for matrix exponential if we're looking for solving a matrix, right? Because actually for most of the application of matrix exponential, we're not really interested in exponential of t, like we're not really interested in exponential of c, but rather like a composition of a vector onto exponential of tc. So we don't need to compute the entire thing. That's pretty much the idea. So so this example over here, okay, this is pretty much done. So this is wait, hold up. Why is there t over there? Oh yes. So there is the matrix exponential is given by this thing, which is given by Okay, so I think there's just a small typo. This is oops, TC. Okay, TC. Yeah. Now let's get to the matrix exponential times a generalized eigenvector. So over here, there's a Jordan chain, and this Jordan chain comes with an expansion that we can handfully use for raise that power raised to like power t, and we can pretty much exponential of TAV1. This is pretty much what we like generally use exponentiation for, because we can solve some really complex like kind of like system of equations using this method. So okay, it does come with a caveat, right? That if you have V1, V1 must be a generalized eigenvector corresponding to lambda. If it's not, you have to decompose it into generalized linear combination of generalized eigenvectors first, and then use those generalized eigenvectors as the basis to set up your Jordan chain. So it all ties together. Matrix exponential and Jordan chains, you would have to use the generalized eigenvectors, which provides you the Jordan chain, which provides you the exponentiation expansion of your e to the exponential of ta. Okay. So this part, solving homogeneous system of differential equation, this part I'm not too sure if it's covered in 2501, but it's definitely covered in 26. So here we have the question, it begs the question that if you have a vector dyt dt equals to ay, with a as some matrix, what is the solution? Or like, how do we express the solution of a? Okay, and generally it's this looks like in the form of a typical kind of like high school maths kx, right? Dx dt equals kx, and the solution to that is basically the same thing, which is x equals e to the t a, I believe, a kt, right, plus c or something like that, with an initial condition of x0. So a times e to the kt, I believe, that's the solution to this differential equation. Now this is similar, okay? This is not a. Let's just use c. Okay, yeah, this is very similar. So, but it's for vectors instead of just single values. So how do we do that? So recall that we have so let's look at an example, right? Recall that if we have this same matrix as previous part, and then we have this generalized eigenvector, and then we have this chain, like we can use this to solve the initial value problem. So first you'll need to look at this eigenvector, generalized eigenvector, and then apply it to exponential of ta. All right, and then this is the solution because of this property over here. That's since we know that the initial condition is in fact this generalized eigenvector, so we can just plug it right in. Okay. Now exponential ta is already calculated. Why is that? Because we know that this matrix is in fact this thing. So we just need to kind of like times it together, and you'll end up with this solution. Okay, this solution over here. So what this does is it bypass all the hassle that you have to do with P, okay, which is the matrix of all of your generalized eigenvectors. But instead you just need one, okay, you just need the one that is in your initial condition. Now if it's not, remember you need to decompose it into linear combination of that. Okay, so this is another example, right? So this is for non-homogeneous, And essentially it's a similar thing, but this equation, okay, so this is definitely in the 2601 category, but basically this next example over here, it's to look at another system of equation, but instead this one has an integrating factor involved, because this is in the form of y dash equals to uy plus some kind of x, right? X of t. So whenever it's in this form, you need to let y equals to some other transformation, and then equate both sides so that y dash and uy would somehow cancel out. And that's pretty much the idea. And we end up with like this new system of equation, which is in terms of one variable. And solving for that, we'll use the Jordan chain for this new matrix, okay? And it's minus a2. So we're given that minus 8, 2, and minus 4 is a generalized eigenvector once again. And then applying that onto the matrix, you get 5, right, minus 6, 6, 6, and then boom, you get 0, 0, 0. So yeah, so pretty much your e to the tc is equated to this generalized eigenvector, but in reverse. So you don't actually need to compute. Yeah, in fact, you don't really need to compute this thing anymore. This thing you can, this thing goes away. Okay, you don't need to do that anymore. You just use this. Okay, exponential of ta is e to the lambda t times v1 plus t v2. Okay, that's what we did over here. Chuck it in, flip this in reverse, plug it in here, flip this, plug it in here. That's the column method. Okay, and it's a lot faster. And observe, okay, yeah, and finally after that part, we just need to observe that, okay, we're looking at e to the minus tc. We're not looking at e to the positive tc. So we just flip the sign by substituting t with minus t because it's a dummy variable. And after that, you just look at, okay, so t e to 5t, I need to times it on top of this thing, and that's what I get, right? So timesing e to the t times e to the 5t here, and you'll end up with this matrix. Oh, sorry, this vector. So this vector is the final solution. And remember, our question is solving for dztt. So we integrate both sides and then getting a constant now here. Now, we're not done yet because z is the substitution factor of e to the tc. We actually need to reconvert it again. So to do that, we just look at e to the tc times this, which is what we do over here. So e to the tc times the first part, e to the tc times second part, and then e to the tc times the integration constant. And then finally, we can recycle our usage of our Jordan chains and just recompute e to the tc again, e to the tc again, and then simplify. That's pretty much it. So yeah, well, this e to the tc times c, we don't really know what that is, so we'll just leave that. But this is one particular solution, okay? One particular solution where c is any kind of constant. So yeah, the summary is we don't really know what c is, but we can kind of provide a we can actually use, it could also be a potential separate Jordan chain that we need to compute if they give us a c. So but we can definitely kind of like redo that and just kind of reapply if they tell us another initial condition for y. But let's just hope that this is not going to be the case, so we don't need to solve for this c. But if you do have to solve for this c, you just have to equate both sides and solve for the initial condition. And that's pretty much it. So is there any questions from the audience? I guess like this topic of matrix exponential is rather computational intensive. So it could confuse some people, but hopefully it's okay. Yep. All right. So, okay, let's just end it here then. If there's no question from the audience. All right, thanks guys. Thanks for listening, and good luck for your finals.